Welcome to the era of the intelligent digital twin. To understand where we are going, we must first understand the bridge between reality and the virtual world. On the left, we have the physical twin, a tangible system, like a jet engine, a manufacturing robot, or an entire smart city. On the right is its digital twin, a precise virtual replica constructed from data. Traditionally, this relationship has been a simulation. We observe the physical world and send data to the digital one to analyze what happened. It is a passive, one-way street, but a true digital twin requires synchronization. It evolves into a two-way conversation. We don't just send data to the model. The model sends control signals back to the physical system, optimizing it in real time. Now, we are witnessing a paradigm shift. By integrating large language models and world models, the digital twin is no longer just a tool, it becomes an autonomous agent. It gains a brain, capable not just of mirroring reality, but of reasoning, planning, and actively managing it. This is the intelligent digital twin, a proactive cognitive system.
To understand how AI transforms this field, we need a map. The paper proposes a unified four-stage framework. At the center, we have the AI-driven digital twin. But how does it come to life? It happens in a continuous cycle. It begins with modeling. Here, we aren't just drawing pictures. We are building mathematical representations denoted here by theta, combining fundamental physics with data-driven neural networks to create a static baseline of the world. Next, we move to mirroring. A model is useless if it's outdated. This stage locks the digital to the physical through real-time synchronization, ensuring our twin reflects reality as it happens, not as it was yesterday. But observation is passive. We need action. This leads to intervening. By minimizing loss functions and running simulations, the AI detects anomalies and suggests optimizations to actively improve the physical system. Finally, the paper introduces the frontier: autonomous management. By integrating large language models and agents, the twin evolves from a tool into a brain, capable of reasoning, planning, and managing the system without constant human oversight. Crucially, this is a loop. The autonomous insights feed back into the modeling phase, refining our understanding and starting the cycle anew. This framework serves as our roadmap for the rest of this video. Building upon the history of simulation, we now enter the first distinct stage of the digital twin lifecycle: modeling. To build a high-fidelity twin, we start with physics-based methods. These are the fundamental equations like partial differential equations that describe the laws of nature governing the system. However, theory isn't enough. We also need data-driven methods, fed by real-time streams of sensor data that capture the messy, unpredictable reality of the physical world. The breakthrough lies in fusing these two. We direct both the rigid laws of physics and the dynamic sensor data into a unified architecture known as physics-informed AI. Here, the AI learns from the data, but is constrained by the laws of physics, ensuring the model is both accurate to reality and scientifically robust. This completes the modeling stage. Once the model is built, we move to the second stage, mirroring. This is where the static model comes to life. Through real-time synchronization, the state of the digital twin represented here in green moves in perfect lockstep with the physical system in blue. The AI continuously updates the twin, ensuring that what you see on the screen is an exact, living mirror of what is happening on the ground, right now. Having established a perfect mirror in stage 2, we now advance to stage 3, intervention. Here, the digital twin evolves from a passive observer into an active guardian. Consider a critical parameter of our system, perhaps engine temperature or structural stress. We define a safety threshold, shown here in red. As time passes, the twin monitors performance. In a traditional setup, we might only react once the line hits the limit, often too late. But an AI-driven twin doesn't just look back, it looks forward. Using predictive modeling, it projects the system's future state, identifying a potential failure before it actually happens. This is the power of predictive analytics. Upon detecting this future risk, the twin initiates an intervention. It sends a feedback signal, an optimization command back to the physical counterpart. The physical system adjusts its parameters in real time, perhaps slowing down a motor or rerouting power to mitigate the risk. The result, the trajectory changes. The potential failure is averted, and operation continues smoothly within safe limits. This closes the loop between the virtual and the real, paving the way for the final stage, full autonomy. Building on the mirroring and intervention capabilities we've just seen, we now reach the pinnacle of this technology. Stage 4. This is autonomous management. Here, we introduce a new, higher-level controller above the digital twin, the cognitive layer. This layer is powered by large language models for logical reasoning and generative world models for imagination. It doesn't just track the present, it envisions the future. Instead of blindly sending commands, the cognitive layer generates complex, what-if scenarios and reasoning strategies, passing them down to the digital twin. The digital twin then acts as a safe sandbox. It simulates these scenarios, virtually testing consequences and optimizing parameters without ever risking the physical equipment. Only once a strategy is proven safe and effective in the digital realm is the optimized action executed on the physical twin. This creates a self-governing system capable of handling unforeseen challenges autonomously. As we look toward the horizon, we envision a comprehensive future ecosystem of digital twin AI. But reaching this state isn't just about adding more data. We face 3 critical hurdles that act as gatekeepers. First, scalability, the sheer computational cost of running massive world models. Second, hallucination, the risk of generative AI fabricating errors. And third, privacy, the absolute necessity of securing sensitive user data. These aren't just theoretical problems, they are active threats. Without robust defenses, high costs limit access, errors destroy reliability, and data leaks erode public confidence. However, current research is turning these shields into pillars. By solving scalability, we gain efficiency. By curing hallucinations, we build trust. And by embedding privacy, we ensure security. This paves the way for a truly interoperable and ethical ecosystem.